This is a sample so you can see how my online teaching is. The derivative is just the process of calculating the slope of a curve by taking 2 points on that curve and making them closer together. Let's first revisit the slope of a straight line. Suppose we have the line y equals x, and we are going to take 2 points. Our first one will have coordinates x sub 1, y sub 1. And our second one will have coordinates x sub 2, y sub 2. Our slope will be y sub 2 minus y sub 1, all divided by x sub 2 minus x sub 1, changing 1 and y over changing x. Now we are going to take the same approach, but this time for the curve x squared, and remember that f of x and y are equivalent, just a way of saying that y is a function of x. Now our first point will have coordinates x, f of x, and our second point will have coordinates x plus delta x. And think of delta x as a small increment in x, as the small distance separating those 2 points. Delta x is a really small number, like 0.0000, even smaller. So our y coordinate will be f of x plus delta x. Now our slope will be same as before, y sub 1, which in this case is f of x plus delta x, minus y sub 1, which is just f of x, all divided by, again just as before, our x sub 2, which is x plus delta x, minus our x sub 1, which is x. We can cancel x with minus x, and we're left with f of x plus delta x minus f of x, all divided by delta x. But this is the slope of the straight line joining the 2 points in that curve. To calculate the slope of the curve, we are going to make the second point closer to the first by making delta x approach 0. And at that point, the slope of the curve will be equal to the slope of the tangent line touching the curve at that point. So the slope of our curve will be the limit as delta x approaches 0 of f of x plus delta x minus f of x, all divided by delta x. And this is the derivative of x, or the change in y over the instantaneous change in x. In other notation, dy over dx. Now that we know all of this, let's apply it. Let's try to find the derivative of our function. So f of x is just x squared, and we are going to obtain f of x plus delta x by replacing x plus delta x in the original function to get x plus delta x all squared. Now the derivative will be, or the slope of the curve will be the limit as delta x approaches 0 of f of x plus delta x, which we calculated before as being x plus delta x all squared, minus f of x, which is just x squared, all divided by delta x. Now we can expand the binomial in the numerator to get x squared plus 2 times x delta x, times plus delta x squared, and minus x squared comes along from the right, and of course all divided by delta x. And now we can cancel x squared with minus x squared, and we left with 2 times x times delta x plus delta x squared, all divided by delta x. And look, we have a common factor in the numerator, delta x. We can factor that out to get delta x that multiplies 2x plus delta x, all divided by delta x. And we finally can cancel delta x in the denominator with the one in the numerator. And all we have left now is the limit as delta x approaches 0 of 2x plus delta x. And now by limit properties, that's just 2x plus 0, which is 2x. That's our derivative. Now let's talk briefly about one of the rules or shortcuts to calculate derivatives that says if I have x elevated to an exponent, its derivative is just the exponent times x, and you subtract 1 from the exponent, for the original exponent. So let's apply this to our function x squared, to our curve. Its derivative is going to be the exponent times x, and you subtract 1 from the original exponent, so to get 2x. Amazing, huh? Just remember, every time that you are using that shortcut, you are taking a limit.